Somewhere on the surface of Mars, a rover named Opportunity continued driving long after its 90-day mission ended, wandering the red dust for nearly 15 years before its final message home. That kind of quiet perseverance, that steady rolling forward across an ancient and silent world, carries something worth holding as the night settles in. These machines, built by human hands and sent impossibly far, have traced wheel tracks across craters and valleys where no wind carries sound, where sunsets glow blue against a butterscotch sky. If these slower journeys help ease the mind toward rest, subscribing means more will arrive whenever they are needed. For now, the story of the Mars rovers waits. Spirit and opportunity, curiosity and perseverance, each one a small explorer on a vast and rust-colored plain. And this is where we begin. Long before any machine left the Earth, long before the first telescope was ground and polished, long before the mathematics of orbits was understood, there was simply the sky. And within that sky, there moved a small point of light that did not behave as the others did. The stars, those fixed and faithful companions of the night, wheeled overhead in their predictable arcs, rising and setting with the seasons. But this particular light wandered. It drifted slowly against the backdrop of constellations, sometimes moving one direction for weeks, then pausing, then doubling back upon itself as if lost in thought, before resuming its original course. The ancients watched this motion with great care, and they gave the wanderer a name, and they wondered what it meant. In the fertile valleys between the Tigris and the Euphrates, in the land we now call Mesopotamia, the Babylonian astronomers kept detailed records of the sky on clay tablets pressed with cuneiform script. They tracked the movements of the planets with remarkable precision, noting their positions night after night, year after year, building a treasury of observations that would span centuries. To them, this red wanderer was Nergal, named for their god of war and pestilence, a deity associated with death and the underworld, with scorching heat and the devastation of battle. The planet's rusty color, visible even to the unaided eye, perhaps suggested blood, or fire, or the parched earth of a land under siege. Whatever the association, Nergal moved through the heavens as an omen, and the priests who watched the skies interpreted its wanderings as messages concerning the fate of kings and empires. Further, along the great river Nile, in the land of Egypt, the same red point of light was known by another name. The Egyptians called it Herdesha, which translates simply as the Red One, a straightforward description of its most obvious quality. Egyptian astronomers, like their Babylonian counterparts, tracked the movements of the planets and incorporated them into their understanding of the cosmos, linking celestial events to the cycles of flooding and harvest that governed their agricultural lives. The color of Mars was unmistakable, a warm, ruddy hue that distinguished it from the cooler lights of the other visible planets. And this color would continue to define humanity's perception of the world for millennia to come. As early as 1534 years before the Common Era, careful observers were noting the peculiar retrograde motion of Mars, that strange apparent reversal in its path across the stars. This motion, we now understand, is simply a consequence of perspective, an illusion created by the Earth overtaking Mars in its orbit around the Sun. much as a faster car on a highway seems to make a slower car appear to drift backward against the distant landscape. But to ancient eyes, without the benefit of this heliocentric understanding, the retrograde loops of Mars were genuinely puzzling. A deviation from the expected order of things that demanded explanation. Various models were proposed over the centuries, some involving complex systems of nested spheres, others invoking epicycles upon epicycles in an ever more elaborate attempt to preserve the assumption that Earth stood motionless at the center of all creation. The centuries passed, and the Red Wanderer continued its patient journey through the stars, observed by generation after generation of watchers who peered upward and wondered. The Greeks associated it with Ares, their own god of war, and the Romans later gave it the name we still use today, Mars, after their equivalent deity. The color remained constant, that distinctive rusty glow, and the wandering continued, and the questions persisted. What was this light, truly? What was it made of? Why did it move as it did? And though no one could answer these questions with certainty, the observations continued, building an ever larger foundation of data upon which later thinkers would construct their theories. In the latter half of the 16th century, on a small island called Ven in the narrow strait between Denmark and Sweden, a nobleman named Tycho Brahe established an observatory unlike any the world had seen. Brahe was a meticulous observer, perhaps the most precise the pre-telescopic era would ever produce, and he devoted himself to measuring the positions of stars and planets with instruments of his own design, large and carefully calibrated devices that could determine celestial positions to within a fraction of a degree. From 1576 to 1597, Brahe and his assistants worked at Uraniborg and later at Sternborg, night after night when the skies were clear, recording the positions of Mars with unprecedented accuracy. Brahe himself did not live to fully interpret his observations, but he bequeathed them to a young mathematician named Johannes Kepler, and it was Kepler who would finally unlock the secret of the Red Wanderer's path. Kepler struggled for years with Brahe's data, attempting to fit the observations of Mars into the traditional circular orbits that astronomers had assumed for centuries. But no matter how he adjusted his calculations, no matter how many minor corrections he applied, the observations refused to match a circular path. The discrepancies were small, only 8 minutes of arc, a tiny fraction of a degree, but Brahe's measurements were too precise to dismiss, and Kepler was too honest to ignore them. Those 8 minutes of arc, he later wrote, would lead to a complete reformation of astronomy. After much labor and many failed attempts, Kepler finally realized that Mars did not move in a circle at all, but rather in an ellipse, with the Sun at one focus. This was the first of his 3 laws of planetary motion, published in 1609, and it was Mars, specifically Mars, whose stubborn refusal to fit the old models had forced this revolution in understanding. The Red Wanderer had taught humanity something profound about the architecture of the solar system. The invention of the telescope in the early 17th century opened new possibilities for observation, and over the following centuries, astronomers turned their instruments toward Mars with increasing curiosity. They could see that it was a disk, not merely a point of light, and they could make out vague markings on its surface. dark and light regions that seemed to shift and change with the seasons. Polar caps of white were observed, growing and shrinking over the Martian year, suggesting perhaps the presence of ice or frost. The planet was clearly a world, a place with geography and weather and seasons of its own, and the question that had been implicit for so long began to be asked more explicitly. Was Mars alive? Did anything grow there? Did anyone live there? In 1877, during a particularly favorable opposition when Mars approached unusually close to Earth, the Italian astronomer Giovanni Schiaparelli conducted a series of careful observations from the Brera Observatory in Milan. Schiaparelli was a skilled observer and a patient one, and he produced detailed maps of the Martian surface, charting the dark and light regions with names drawn from classical geography and mythology. But it was one particular feature of his observations that would capture the public imagination more than any other. Schiaparelli reported seeing long, linear features crossing the Martian surface, and he called them canali, an Italian word that simply means channels, a neutral term that might describe any natural groove or watercourse. But when his observations were translated into English, canali became canals, a word with very different connotations, suggesting not natural formations but artificial constructions, waterways built by intelligent beings for some deliberate purpose. The idea of canals on Mars seized the imagination of the late 19th century, and no one embraced it more enthusiastically than the American astronomer Percival Lowell. Lowell came from a wealthy and distinguished Boston family, and he had the means to pursue his obsessions on a grand scale. In 1894, he established an observatory in Flagstaff, Arizona, at an elevation of over 7,000 feet, specifically to study Mars. The thin, dry air of the Arizona high desert provided excellent observing conditions, and Lowell devoted the remaining years of his life to mapping the Martian canals in ever greater detail. He produced chart after chart showing an intricate network of straight lines crisscrossing the planet, and he developed an elaborate theory to explain them. Mars, he proposed, was a dying world, an ancient planet whose water was slowly disappearing. The canals were the desperate engineering projects of an advanced civilization, attempting to transport water from the melting polar caps to the arid equatorial regions. It was a romantic vision, tragic and compelling, and it captured the public imagination as few scientific ideas ever have. Lowell wrote books and gave lectures, spreading his theory of a dying Mars inhabited by intelligent beings struggling against the inevitable decline of their world. Other astronomers were more skeptical, and many reported that they could see no canals at all, or only vague, irregular markings that bore no resemblance to Lowell's precise geometric networks. The debate continued for decades, but in the popular mind, the image of Mars as a world of canals and ancient civilizations took firm hold. Science fiction writers embraced the idea enthusiastically, and stories of Martians, sometimes friendly, sometimes hostile, became a staple of the genre. The Red Wanderer had become, in the human imagination, not merely a light in the sky or a subject of astronomical study, but a neighboring world where minds like our own might gaze back at Earth and wonder about us in return. We know now that the canals were an illusion, an artifact of the human eye's tendency to connect, scattered, indistinct markings into continuous lines. The Mars revealed by spacecraft is a world of craters and volcanoes, of ancient river valleys and vast dust storms, but not of geometric canals. Lowell was wrong about the details, profoundly wrong. Yet there was something right about the impulse that drove his work. The simple human desire to know whether we are alone. Is Mars alive? The question haunted astronomers for generations, and in a sense it haunts us still, though we now ask it with more precision and with better tools for finding the answer. There is one detail about Mars that has always seemed particularly tantalizing to those who study it, a coincidence so close that it almost seems designed to encourage our curiosity. A day on Mars, a single rotation of the planet on its axis, lasts approximately 24 hours and 37 minutes. This is so close to the length of an Earth day that the similarity is striking, a mere 37 minutes separating the rhythms of the two worlds. If you were to live on Mars, your body's circadian rhythms, evolved over millions of years to match the 24-hour cycle of Earth, would find the Martian day only slightly misaligned with their expectations. You would drift slowly out of sync, but only slowly, and the experience of day and night would feel almost familiar. This similarity was known long before the space age, calculated from observations of surface features rotating in and out of view, and it added to the sense that Mars was somehow a kindred world, a place that might not be so different from home. And so, for centuries, humanity gazed upward at that rusty beacon, that red point of light wandering through the constellations, and wondered. The Babylonians saw an omen, the Egyptians saw a color, Tycho Brahe saw a challenge to his instruments, Kepler saw a mathematical puzzle, Schiaparelli saw channels, and Lowell saw a civilization. Each generation brought its own questions and its own assumptions, its own hopes and its own fears. And each generation added something to the long human conversation about the red planet. The simple question that lay beneath all the others, the question that would eventually drive machines across the void to land upon the Martian surface and roll across its ancient terrain, was always the same. Is Mars alive? Does anything stir in that rusty soil? And if the answer is no, was it ever otherwise? These were the questions that waited, patient as the planet itself, for the day when we would finally go and see for ourselves. The story of Mars exploration is, in many ways, a story of patience and persistence in the face of repeated disappointment. And before we arrive at the rovers that would eventually roll across the dusty plains of that distant world, we must first acknowledge the long and difficult road that came before them, a road marked by failure far more often than success, by spacecraft that fell silent or tumbled back to Earth or simply vanished into the void between worlds without explanation or farewell. In the early 1960s, when the space age was still young and the moon had not yet felt the weight of human footsteps, the Soviet Union turned its attention toward Mars with characteristic ambition and determination, launching a series of missions that would test the very limits of what was possible with the technology of that era. The first of these attempts came in October of 1960, when two spacecraft known collectively as the Mars 1M series were prepared for launch from the Baikonur Cosmodrome in Kazakhstan. Their destinations, set for the Red Planet, some 55 million kilometers away at its closest approach. Neither spacecraft reached orbit around Earth, let alone Mars, as the third stage of their launch vehicles failed in both cases, sending the probes tumbling back toward the planet they had hoped to leave behind. These failures were kept secret for many years, as was common practice during that time, and the spacecraft were never officially acknowledged until decades later, when Soviet records became available to historians. It was an inauspicious beginning to humanity's attempts to reach Mars, though certainly not an unusual one, for the exploration of space has always demanded that we accept failure as a necessary companion to progress. The difficulties continued throughout the 1960s for both the Soviet Union and the United States, with mission after mission encountering problems that ranged from launch failures to communication losses to trajectory errors that sent spacecraft sailing past their intended targets into the endless darkness beyond. The Americans experienced their own share of heartbreak in November of 1964, when Mariner 3 was launched toward Mars, carrying instruments designed to photograph the planet's surface and measure the properties of interplanetary space. The spacecraft was encased in a protective shroud, a metal covering designed to shield the delicate instruments from the forces and heat of passing through Earth's atmosphere. And this shroud was meant to separate and fall away once the spacecraft had reached the vacuum of space. But the shroud did not separate as planned, remaining stubbornly attached to the spacecraft and preventing the solar panels from deploying to generate the electrical power that Mariner 3 needed to survive. Without power, the spacecraft's batteries drained within hours, and Mariner 3 fell silent, drifting away from Earth in a slowly widening orbit around the Sun, its cameras never capturing a single image of the world it had been built to study. The engineers at the Jet Propulsion Laboratory worked frantically to understand what had gone wrong, knowing that a second spacecraft, Mariner 4, was already being prepared for launch just 3 weeks later, and they identified the problem as a flaw in the shroud's design that prevented the explosive bolts from functioning correctly in the vacuum conditions. The repairs were made, the shroud was redesigned, and Mariner 4 launched successfully on November 28 of 1964, beginning a journey of 228 days across the vast distance between Earth and Mars. This spacecraft would become the first to successfully fly past Mars and return data to Earth, a genuine triumph after so many disappointments. And yet the images it returned would bring a different kind of disappointment to the scientists who had spent their careers dreaming of what Mars might hold. On July 14th of 1965, Mariner 4 swept past Mars at a distance of roughly 10,000 kilometers, its television camera clicking away as it captured 22 photographs of the planet's surface. Each image built up slowly from the faint radio signals traveling across the interplanetary distance at the speed of light. The photographs took nearly a week to transmit in their entirety, and as engineers at the Jet Propulsion Laboratory decoded the first images by hand, coloring in the pixels on paper with crayons while they waited for the computers to process the full data, they saw something that few had expected. Mars appeared as a cratered, barren, apparently dead world, more similar to Earth's moon than to the vibrant planet that generations of observers had imagined when they gazed through their telescopes and saw what they believed were seasonal changes in vegetation or the straight lines of irrigation canals built by intelligent beings. The canals, of course, had never existed except in the minds of hopeful observers. Most notably, the Italian astronomer Giovanni Schiaparelli, who, in 1877, had mapped features he called canali, using the Italian word for channels, and the American astronomer Percival Lowell, who built an entire observatory in Arizona dedicated to studying Mars, and who published books describing an ancient civilization struggling to survive on a dying world by engineering vast waterways to carry water from the polar ice caps to the parched equatorial regions. These ideas had captured the public imagination for decades and had inspired countless works of fiction, from the scientific romances of H.G. Wells to the adventure stories of Edgar Rice Burroughs. And many scientists, while skeptical of the more fanciful interpretations, had genuinely hoped that Mars might harbor some form of life, perhaps vegetation that changed color with the seasons as the polar caps advanced and retreated. The images from Mariner 4, showing only craters and desolation, were therefore received with a certain quiet sadness in the scientific community, though the data was far too limited to draw any definitive conclusions about the entire planet from just 22 photographs covering roughly 1% of the surface. The Soviet Union continued its efforts throughout the 1960s and into the 1970s, achieving some successes among the many failures, though none of its Mars missions would fully accomplish all of their intended objectives until much later. The pattern of failure was so consistent that Mars acquired a grim reputation among spacecraft engineers and mission planners, who began to speak half-jokingly of the Great Galactic Ghoul, an imaginary creature that supposedly lurked near Mars and devoured spacecraft that ventured too close. The statistics supported this dark humor, for by the end of the 20th century, roughly 2/3 of all missions sent to Mars had failed in one way or another, earning the Red Planet the unofficial title of the Death Planet for robotic explorers. Some of these failures could be attributed to the inherent difficulty of the task. For reaching Mars required launching a spacecraft with sufficient velocity to escape Earth's gravity, then navigating across tens of millions of kilometers of empty space using only radio signals and mathematical calculations, then slowing down enough to enter orbit or descend to the surface, all while enduring the radiation and thermal extremes of the interplanetary environment. Other failures resulted from human error, from software bugs, from manufacturing defects, from the simple reality that space exploration pushes technology to its absolute limits, and sometimes those limits prove insufficient. The Americans achieved their greatest Mars success of the era in 1976, when two spacecraft named Viking 1 and Viking 2 not only entered orbit around Mars, but each deployed a lander that descended safely to the surface, becoming the first spacecraft to successfully land on Mars and transmit data back to Earth. Viking 1 touched down on July 20th, 1976, in a region called Cres Planitia, the Plain of Gold, and was soon followed by Viking 2, which landed on September 3rd of that same year in a northern region called Utopia Planitia. These landers carried cameras that would return thousands of photographs showing a rocky, rust-colored landscape beneath a butterscotch sky, along with instruments to measure weather conditions, analyze the composition of the soil, and most importantly, to search for signs of life in the Martian dirt. The Viking biology experiments represented the most sophisticated attempt ever made to detect life beyond Earth, and they were the subject of intense anticipation and even more intense debate in the years that followed. 3 experiments were designed to search for life in the Martian soil, each based on different assumptions about what Martian organisms might be like and how they might behave when exposed to nutrients or other stimuli. The labeled release experiment, designed by a scientist named Gilbert Levin, involved adding a drop of nutrient solution containing radioactive carbon to a sample of Martian soil and then monitoring the air above the sample for radioactive carbon dioxide, which would indicate that something in the soil was metabolizing the nutrients and releasing gas as a byproduct, just as living organisms on Earth do. When the experiment was conducted, the results were surprising and, to Levin, deeply exciting. For the instrument did indeed detect a rapid release of radioactive gas from the Martian soil, a result that would have been considered strong evidence of biological activity if it had been obtained in an Earth laboratory. However, the other 2 experiments produced results that were more ambiguous or negative. And perhaps most importantly, another instrument on the lander called the gas chromatograph mass spectrometer, which was designed to detect organic molecules in the soil, found no evidence of the carbon-based compounds that are the building blocks of all known life. This absence of organic molecules led most scientists to conclude that the labeled release results must have been caused by some unusual chemical reaction in the Martian soil rather than by living organisms, perhaps involving highly reactive compounds called peroxides that might form in the harsh radiation environment on the Martian surface. Gilbert Levin never accepted this interpretation, and he would spend the remaining decades of his life arguing that his experiment had indeed detected life on Mars, that the scientific community had been too quick to dismiss the positive results, and that the failure to find organic molecules could be explained by other factors that had not been fully considered. His persistence was remarkable and perhaps admirable, though it placed him increasingly at odds with the mainstream scientific consensus. And the question of what the Viking landers truly found in the Martian soil remains a subject of occasional discussion, even today. A mystery that has never been fully resolved to everyone's satisfaction. Whether Levin was a visionary who recognized something that others missed, or simply a scientist who became too attached to a particular interpretation of ambiguous data, is a question that only future missions, perhaps with more sophisticated instruments, will be able to answer definitively. After Viking, the exploration of Mars entered a long period of relative quiet, with no American spacecraft visiting the planet for over 17 years. A gap that reflected shifting priorities in space exploration, budgetary constraints, and perhaps a certain loss of enthusiasm following the disappointment of finding a world that seemed so barren and lifeless compared to the hopes of earlier generations. The Soviet Union continued launching missions, with mixed results, though none achieved the scientific returns of the Viking program. One of the most ambitious Soviet missions, Mars 96, was launched in November of 1996 and represented a massive international effort involving scientific instruments from multiple countries. But the spacecraft's 4th stage failed to ignite properly, and the entire mission fell back to Earth within hours of launch, crashing somewhere in the Pacific Ocean or possibly in the mountains of South America. Its exact fate never determined with certainty. The Americans attempted to return to Mars in 1993 with a mission called Mars Observer, a large and sophisticated spacecraft carrying 7 scientific instruments designed to map the planet's surface and study its atmosphere and magnetic field in unprecedented detail. The spacecraft launched successfully in September of 1992 and spent 11 months traveling toward Mars, its systems functioning normally throughout the long journey. And scientists and engineers grew increasingly excited as the moment of orbit insertion approached. Then, on August 21st of 1993, just 3 days before Mars Observer was scheduled to fire its engines and enter orbit around Mars, the spacecraft fell silent. No telemetry was received, no signals were detected, and despite extensive efforts to re-establish contact, Mars Observer never responded. An investigation concluded that the most likely cause was a rupture in a fuel line, causing propellant to leak and possibly sending the spacecraft spinning out of control, though without any data from the spacecraft during its final moments. The exact cause could never be known with certainty. Nearly $1 billion and years of work had simply vanished into the silence between worlds. Another sacrifice to the great galactic ghoul that seemed to guard Mars against human curiosity. By the mid-1990s, then, the exploration of Mars stood at a crossroads, marked by extraordinary achievements like Viking, but also by an accumulation of failures that made every new mission seem like a gamble against unfavorable odds. The question of whether life had ever existed on Mars remained stubbornly unanswered, with the Viking results still debated and no new data to resolve the controversy. Reaching Mars was extraordinarily difficult, more difficult than reaching the Moon or Venus or any other body in the inner solar system. And the engineers and scientists who devoted their careers to this endeavor knew that failure was always lurking somewhere in the complex chain of events that had to proceed perfectly for a mission to succeed. Yet they also knew that Mars held answers to some of the most profound questions that humans have ever asked. Questions about the origins of life and the possibility of other worlds harboring living things. And so they continued their work, learning from each failure, refining their designs, and preparing for the next attempt to cross the great distance and unlock the secrets of the Red Planet. In the quiet corridors of the Jet Propulsion Laboratory in Pasadena, California, where the hum of computers and the soft shuffle of engineers moving between workstations creates a kind of constant, soothing background murmur, there began to take shape in the late 1990s a pair of machines that would eventually travel farther from home than any wheeled vehicle had ever gone before. And the story of how they came to be built is itself a gentle tale of patience, of persistence, and of the slow accumulation of years of careful planning that is so characteristic of the way we explore the worlds beyond our own. The idea for what would become the Mars Exploration Rover program had its earliest roots in the mind of a planetary scientist named Steve Squyres, who worked at Cornell University in the state of New York, where he spent his days studying the surfaces of distant planets and moons through the images and data returned by various spacecraft. And it was in 1987, a full 16 years before the rovers would actually launch, that Squyres first proposed sending a robotic rover to Mars carrying instruments that could examine rocks and soil in ways that no previous mission had attempted. Though the path from that initial proposal to the actual construction of the spacecraft would prove to be long and winding, filled with setbacks and delays that required the sort of patient determination that is perhaps the most essential quality of anyone who wishes to explore other worlds. The program that eventually emerged from those years of planning was given the rather straightforward name of Mars Exploration Rover, often shortened simply to MER, and it called for not one but 2 identical rovers to be sent to Mars, landing in different locations so that scientists could study 2 separate regions of the planet and thereby double their chances of making significant discoveries. And this decision to build twin spacecraft also provided a measure of redundancy, since the loss of one rover would not mean the complete failure of the mission, a consideration that is always present in the minds of those who design missions to other planets, where so many things can go wrong and where there is no possibility of sending a repair crew if something breaks. The construction of the rovers took place at the Jet Propulsion Laboratory, which has been responsible for most of America's robotic missions to other planets since the earliest days of space exploration. And the facility sits nestled against the San Gabriel Mountains in a suburb of Los Angeles, where the climate is mild and the grounds are dotted with buildings that house some of the most sophisticated spacecraft assembly rooms in the world. And it was in these clean rooms where technicians wear special suits to prevent even the smallest particles of dust from contaminating the sensitive equipment, that spirit and opportunity slowly took shape over a period of several years, each component carefully designed, tested, redesigned when necessary, and tested again before being integrated into the growing spacecraft. Each of the twin rovers, when fully assembled, weighed approximately 185 kilograms, which is roughly the weight of a large motorcycle, though the rovers were considerably more compact, standing only about 1.5 meters tall when their masts were fully extended, and their 6 wheels, each powered by its own electric motor, gave them the appearance of something between a golf cart and a mechanical insect, with their solar panels spread out like wings to gather the faint sunlight that reaches the Martian surface, and their instrument-laden arms folded against their bodies like the limbs of a sleeping creature waiting to be awakened. The scientific instruments carried by each rover represented the culmination of decades of development in the field of planetary science, and among the most important of these was the panoramic camera, known affectionately as PanCam, which was designed by a scientist named Jim Bell, who was a colleague of Steve Squires at Cornell University. And this camera system consisted of 2 cameras mounted on the rover's mast, positioned like a pair of eyes that could look out across the Martian landscape and capture images in multiple wavelengths of light, including some that are invisible to human eyes. And these images would allow scientists back on Earth to study the colors and textures of rocks and soil in exquisite detail, searching for clues about the geological history of the landing sites. Another instrument mounted on the mast was the Miniature Thermal Emission Spectrometer, known as Mini-TES, which was designed to detect the infrared radiation emitted by rocks and soil. And since different minerals emit infrared light in characteristic patterns, this instrument could identify the composition of materials from a distance, allowing the rover team to decide which rocks were most worthy of closer investigation. And this capability would prove invaluable in the years ahead. when the rovers would traverse landscapes strewn with countless rocks, and the scientists would need some way of choosing where to direct the rover's limited time and energy. At the end of each rover's robotic arm, which could extend outward and position instruments with remarkable precision, there were additional tools for examining rocks up close, including a Mossbauer spectrometer, which is a specialized instrument that can identify iron-bearing minerals by measuring how they absorb gamma rays. And this technique, named after the German physicist Rudolf Mossbauer, who discovered the underlying principle in the 1950s, would prove particularly useful for understanding the history of water on Mars, since certain iron minerals form only in the presence of water, and their detection would provide strong evidence that liquid water once flowed on the Martian surface. There was also the rock abrasion tool, known by its initials as RAT, which was a small grinding wheel that could be pressed against the surface of a rock to wear away the outer layers that had been altered by exposure to the Martian atmosphere, revealing the fresh, unweathered material beneath. And this capability was important because the outer surface of a rock can be quite different in composition from its interior, and scientists studying Mars wanted to know what the rocks were really made of, not just what their weathered exteriors looked like after millions of years of exposure to the thin Martian air and the ultraviolet radiation that streams unfiltered to the surface. As the rovers neared completion in the spring and early summer of 2003, the teams of engineers and scientists who had worked for years to bring them to this point began to prepare for the launch campaign, which would take them to Cape Canaveral in Florida, where the Delta II rockets that would carry the spacecraft to Mars were being readied on their launch pads. And there was a particular urgency to this phase of the mission because the window for launching spacecraft to Mars opens only once every 26 months. When the relative positions of Earth and Mars make the journey possible with a reasonable amount of fuel, and if this window were missed, the rovers would have to wait in storage for over 2 years before the next opportunity arose. The first of the twin rovers, Spirit, was launched on the 10th of June in 2003, rising from Launch Complex 17 at Cape Canaveral atop a pillar of flame and smoke that gradually diminished to a bright point of light ascending into the Florida sky. And for those who had worked on the mission for so many years, watching this moment brought a complex mixture of emotions that is difficult to describe, but which anyone who has ever devoted years of their life to a single project might understand. The relief that the work had reached this milestone, combined with the knowledge that so much could still go wrong in the months ahead. Opportunity followed 3 weeks later, launching on the 7th of July from the same complex, and with both spacecraft safely on their way to Mars. The mission entered what is known as the cruise phase, a period of approximately 6 months during which the rovers, still folded up inside their protective aeroshells, coasted through the vacuum of interplanetary space. And during this time, the spacecraft required only occasional adjustments to their trajectories, small firings of their thrusters to ensure that they would arrive at precisely the right point above the Martian atmosphere when the time came to begin their descent. The choice of where to land the rovers had been the subject of extensive study and sometimes vigorous debate among the scientists involved in the mission. And in the end, 2 sites were selected that represented different types of terrain and different scientific questions to be answered, with Spirit heading for a large impact crater named Gusev, which lies just south of the Martian equator and which scientists believed might once have been the site of an ancient lake, since a long channel called Ma'adim Vallis appears to flow into the crater from the south, suggesting that water might once have pooled there. And if sediments deposited by this water could be found and examined, they might reveal much about the history of water on early Mars. Opportunity was aimed at a region called Meridiani Planum, a broad, flat plain on the opposite side of the planet from Gusev, where orbital observations had detected the presence of a mineral called grey hematite, which on Earth is often associated with the presence of water. And this detection, made by an instrument aboard the Mars Global Surveyor spacecraft that had been orbiting the planet since 1997, suggested that Meridiani might be an ideal place to search for evidence of past water, and the flat terrain also made it a relatively safe place to land, since the bouncing airbag system that would deliver the rover to the surface worked best on level ground, free of large rocks. The engineers who designed the landing system knew that getting a spacecraft safely to the surface of Mars is one of the most challenging tasks in all of space exploration, and they sometimes referred to the entry, descent, and landing sequence as the 6 minutes of terror, because that is approximately how long the process takes from the moment the spacecraft first touches the upper atmosphere to the moment it comes to rest on the surface. And during those 6 minutes, there is nothing that anyone on Earth can do to help, since radio signals take several minutes to travel between the planets, and any problem that arose would have to be solved by the spacecraft's own computers before any signal could reach Earth. The landing sequence began when the spacecraft, still protected by its aeroshell, slammed into the upper atmosphere of Mars at a speed of roughly 20,000 kilometers per hour, and the heat shield on the bottom of the aeroshell absorbed the intense heat generated by this atmospheric entry, reaching temperatures that would melt most metals, while the air resistance gradually slowed the spacecraft to a more manageable speed. And this phase of the landing was a delicate balance, since the Martian atmosphere is thin enough that it cannot slow the spacecraft sufficiently on its own, yet thick enough to generate dangerous amounts of heat and aerodynamic stress. When the spacecraft had slowed to about 1,600 kilometers per hour, a large parachute deployed from the top of the aeroshell, further reducing the speed, and then the heat shield separated and fell away, exposing the lander and rover within, and a radar system began measuring the distance to the surface, preparing for the final stages of descent. And this is when the truly remarkable part of the landing sequence began, a system that had never been used on Mars before the 1997 Pathfinder mission, and which still seems almost magical in its simplicity and its audacity. Just seconds before touchdown, large airbags inflated around the entire lander, encasing it in a cocoon of tough fabric that resembled an enormous cluster of beach balls. And at the same moment, small retro-rockets fired to slow the descent even further. And then the lander was simply released, falling the final distance to the surface. And when it hit the ground, the airbags absorbed the impact and the entire package bounced back into the Martian sky, sometimes reaching heights of several stories before falling back down and bouncing again. And this process could repeat as many as 28 times, with the lander tumbling and rolling across the landscape until it finally came to rest. The engineers had tested this system extensively in laboratories and vacuum chambers on Earth, dropping test articles from high altitudes and watching them bounce across desert terrain. And they had run countless computer simulations to ensure that the airbags could withstand the sharp rocks that might be waiting at the landing site. And yet, there was always the knowledge that Mars itself might have surprises in store that no simulation could predict. And so, as the landing dates approached in January of 2004, the mission team could only wait and hope that their years of careful preparation would prove sufficient for the challenge ahead. The planned mission duration for each rover was 90 Martian days, which are called sols and are about 40 minutes longer than Earth days. And this relatively modest lifespan was based on calculations of how long the solar panels would continue to produce enough electricity to keep the rovers functioning, since engineers expected that Martian dust would gradually accumulate on the panels and reduce their power output. And after 90 sols, the rovers were expected to fall silent, their batteries drained and their electronics frozen in the bitter Martian cold. But, as events would later demonstrate, these predictions significantly underestimated the resilience of the little machines that were now hurtling through the darkness of space toward their distant destination. On the 3rd day of January in the year 2004, in the very early hours of the morning, according to Pacific Standard Time, a small robotic spacecraft wrapped in airbags bounced across the surface of another world, tumbling and rolling until it finally came to rest on the dusty red plains of a region called Gusev Crater. This was Spirit, the first of 2 identical rovers sent by NASA to explore the Martian surface. And after a journey of nearly 7 months through the vast and silent darkness of interplanetary space, its wheels were at last touching the soil of Mars. The landing had been successful, which is to say that an extraordinarily complex sequence of events had unfolded precisely as intended, with parachutes deploying and retrorockets firing and airbags inflating, all within a matter of minutes, while anxious engineers on Earth could do nothing but wait and hope and trust in the machinery they had built. At the Jet Propulsion Laboratory in Pasadena, California, the mood in Mission Control was one of barely contained tension as the final signals came through, indicating that Spirit had survived its violent arrival. When the confirmation arrived, the room erupted into celebration, engineers embracing one another and pumping their fists in the air, some wiping tears from their eyes, others simply standing in stunned relief that the years of work and worry had culminated in this moment of triumph. Among them was Steve Squires, the principal investigator of the rover science mission, a planetary geologist who had spent nearly 2 decades championing this project, shepherding it through funding battles and technical challenges and the ever-present threat of cancellation. For Squires, the landing was not merely a professional achievement, but something far more personal, the fulfillment of a vision he had carried since he was a young researcher dreaming of touching Mars. His reaction was visceral and emotional, the kind of response that comes when something you have worked toward for so long finally becomes real, and in his face one could see both joy and exhaustion, relief and the dawning awareness that the real work was only just beginning. 3 weeks later, on the 24th of January, the scene repeated itself with the landing of Opportunity, Spirit's twin, on the opposite side of Mars in a region called Meridiani Planum. The engineers at JPL went through the same nerve-wracking hours of waiting, the same desperate hope that the airbags would function and the lander would survive. And once again, the news was good. Opportunity had arrived safely, settling into its final resting position after bouncing across the Martian surface, and the celebration at Mission Control was perhaps even more exuberant the second time, for it seemed almost impossible that both rovers had made it through, that the universe had been so generous after all the things that could have gone wrong. The statistics of Mars exploration were not encouraging, with roughly half of all missions to the planet having ended in failure. And yet, here were two American rovers, both healthy, both ready to begin their work, separated by thousands of kilometers, but united in purpose. What happened next with Opportunity was the kind of coincidence that scientists rarely dare to hope for. The sort of stroke of fortune that seems almost too perfect to be believed. When the rover's cameras first opened and began transmitting images back to Earth, the team discovered that Opportunity had landed inside a small impact crater, a shallow depression perhaps 20 meters across, and within this crater the walls were lined with exposed bedrock, layers of ancient Martian rock jutting out from the soil as if placed there deliberately for scientific examination. Steve Squires, upon seeing the images, described the landing as a hole-in-one, borrowing the language of golf to express just how improbable and how fortunate this outcome was. The rovers had been designed to drive across the Martian surface, searching for interesting rocks, potentially traveling for weeks or months before finding suitable targets for their instruments. And yet, Opportunity had come to rest in what amounted to a geological gift, surrounded on all sides by exactly the kind of material the mission had been sent to study. The crater would later be named Eagle Crater, and it would prove to be one of the most scientifically valuable sites ever explored on Mars. But in those first hours, the team simply marveled at their luck, at the randomness that had deposited their precious rover in precisely the right spot. Spirit's first images were different but no less remarkable, showing a landscape of rusty orange soil stretching toward the horizon, where a range of distant hills rose against the pale Martian sky. These were the Columbia Hills, named in honor of the 7 astronauts who had perished in the Space Shuttle Columbia disaster less than a year earlier, and they would become Spirit's primary scientific target in the months and years to come. But in those early days, the hills were merely a tantalizing presence on the skyline, beckoning the rover forward even as the team worked through the careful process of checking systems and preparing for the first drive. The images that Spirit sent back were crisp and clear, revealing a world that was at once familiar and utterly alien, with rocks scattered across the surface and dust devils occasionally visible in the distance. Swirling columns of Martian atmosphere made visible by the fine particles they carried. For millions of people on Earth who followed the mission through news reports and internet updates, these images were windows into another world, a chance to see Mars not as a point of light in the night sky, but as a real place with real terrain. A place where a small robot was now trundling about on behalf of all humanity. The early days of Spirit's mission, however, were not without serious difficulty. On the 18th Martian day of operations, known as Sol 18 in the mission's terminology, something went terribly wrong with the rover's computer systems. Spirit began behaving erratically, failing to respond to commands, resetting itself repeatedly, and sending back garbled and incomplete communications. The engineers at JPL struggled to understand what was happening. Their carefully crafted rover suddenly behaving like a patient in the grip of a fever, confused and unresponsive. After days of careful analysis, the team determined that the problem lay in the rover's flash memory system, a type of computer storage that retains information even when power is turned off. The memory had become corrupted, filled with an accumulation of files that the rover's software was attempting to access each time it booted up, and this process was consuming so much of the rover's computational resources that it could not function properly. Some at JPL described the malfunction as a kind of amnesia, the rover unable to remember what it was supposed to be doing, lost in an endless loop of confusion. The fix, when it came, was elegant in its simplicity, but terrifying in its execution. The team would need to reformat Spirit's flash memory, essentially erasing and rebuilding the storage system. And they would need to do this from a distance of more than 170 million kilometers, with signals taking many minutes to travel between Earth and Mars. There would be no second chances, no opportunity to physically intervene if something went wrong, and the entire operation would have to be conducted through the same unreliable communication link that had been causing so much trouble. The engineers worked methodically, uploading new software commands and carefully guiding the rover through the reformatting process. And after several tense days, the procedure was successful. Spirit's memory was cleared, its systems were stabilized, and the rover returned to health, ready to resume its scientific mission. It was a near miss, a reminder that even the most sophisticated machinery can falter in ways that no one anticipates. And for the team at JPL, it was both a relief and a lesson in the fragility of their creation. Meanwhile, Opportunity was making discoveries almost from the moment it opened its eyes. Among the most striking features visible in the rover's early images were small spherical objects scattered across the Martian soil. Dark bluish-grey nodules about the size of peppercorns, embedded in the rock and lying loose on the ground. The science team, with the affectionate informality that often characterizes planetary missions, took to calling these objects blueberries, and they would prove to be one of Opportunity's most significant finds. Later analysis would reveal that the blueberries were hematite spherules, tiny balls of iron-rich mineral that had formed in the presence of liquid water, perhaps billions of years ago, when Mars was a warmer and wetter world. Their presence at Meridiani Planum was one of the reasons this landing site had been chosen, for orbiting spacecraft had detected the spectral signature of hematite from above, and now Opportunity was seeing the source of that signal up close, scattered across the landscape like geological confetti. Spirit, too, was finding curiosities in the Martian soil, including a peculiar surface texture that the team came to call the magic carpet. In certain areas, the uppermost layer of soil appeared to have been lifted and folded back upon itself, creating a wrinkled, almost fabric-like appearance that was unlike anything seen on Earth. The exact cause of this texture remained uncertain, though scientists speculated that it might be related to the interaction of fine Martian dust with the thin atmosphere, perhaps involving electrostatic forces or the sublimation of subsurface ice. Whatever its origin, the magic carpet was a reminder that Mars, for all its superficial resemblance to terrestrial deserts, was a world with its own unique processes and phenomena. a place where familiar geological rules might not always apply. The first drives of both rovers were cautious affairs, with each wheel revolution monitored closely by engineers on Earth who understood that a single misstep could end the mission. The rovers had been designed to traverse rocky terrain and climb modest slopes. But the Martian surface was unpredictable, and no amount of testing on Earth could fully simulate the conditions of another planet. Spirit took its first tentative rolls forward on Sol 12, moving just a few meters before stopping to take stock of its surroundings. And Opportunity followed suit a few days after its own landing, easing off its lander platform and onto the red soil of Meridiani Planum. For the millions of people following along at home, these early drives were moments of quiet wonder. The realization that human-built machines were now exploring another world in real time, sending back images and data that anyone with an internet connection could access. The rovers themselves were marvels of engineering, each one standing about the height of a human child and weighing around 180 kilograms. Though, on Mars, with its weaker gravity, they weighed considerably less. Their 6 wheels were designed for traction and stability, capable of turning independently to allow the rovers to pivot in place or clamber over obstacles, and their solar panels spread out like wings to capture the wan Martian sunlight. Each rover carried a suite of scientific instruments mounted on a robotic arm, including a microscopic imager for studying fine details, a spectrometer for analyzing rock compositions, and a grinding tool for exposing fresh rock surfaces beneath the dusty exterior. At the top of a tall mast sat a pair of cameras that served as the rover's eyes, providing stereoscopic vision that allowed engineers to navigate the terrain and scientists to examine distant features. As the days turned into weeks and the weeks into months, Spirit and Opportunity settled into a routine of exploration, each Sol bringing new images and new data, each drive revealing fresh wonders. The Columbia Hills grew steadily closer in Spirit's cameras, while Opportunity methodically examined the exposed bedrock of Eagle Crater, finding layers and textures that told of ancient water. The engineers at JPL became adept at driving their rovers by remote control, planning each day's activities with care and adapting to the inevitable surprises that Mars provided. And on Earth, the public followed along with a fascination that exceeded anything the mission planners had anticipated, finding in these small robots a kind of companionship, a connection to a distant world that felt somehow personal and intimate. And so we turn now to the careful work of reading ancient watermarks, the quiet detective story that unfolded grain by grain across the Martian surface, as 2 patient machines examined rocks that had been waiting for billions of years to share their secrets with anyone who might come along to look. When scientists designed the Mars exploration rovers, they equipped them with tools borrowed from the earthly practice of geology, instruments for grinding away the weathered surfaces of rocks, spectrometers for identifying minerals, microscopic imagers for studying textures too small for any camera to capture from a distance. These were the tools of a field geologist, shrunk down and attached to the end of a robotic arm, and they would be used to pursue a question that had lingered in human curiosity for more than a century, which was whether Mars had ever known the presence of liquid water, that remarkable substance we understand to be so necessary for the chemistry of life as we know it on Earth. The evidence would come not in dramatic floods or sudden revelations, but in the patient accumulation of small details. Mineral signatures and rock textures and chemical compositions that together would tell a story of a planet that had once been rather different from the cold and desiccated world we observe today. Opportunity landed in a small impact crater called Eagle Crater, a depression perhaps the size of a tennis court that had punched through the Martian surface and exposed layers of bedrock along its inner walls. The rover's cameras returned images of this outcrop, and scientists noticed immediately that the rocks had a peculiar appearance, a fine-grained texture unlike the volcanic basalts that make up so much of the Martian crust. They named this outcrop El Capitan, and over the following weeks, Opportunity would examine it with the methodical thoroughness of a geologist who has nowhere else to be and all the time in the world to look. The first thing the rover's microscopic imager revealed was a pattern in the rock that geologists call cross-bedding, a series of fine layers arranged at angles to one another, creating a herringbone appearance when viewed in cross-section. On Earth, such patterns form in very specific ways, primarily when sediments are deposited by flowing water or by wind, and the scale and geometry of the cross-bedding at El Capitan suggested that these particular patterns had formed in shallow water, perhaps a few centimeters deep, rippling across a surface and leaving behind the telltale signature of its passage in the arrangement of tiny grains. This alone was suggestive, but the rover found more. Scattered through the rock were small, spherical objects, perhaps a few millimeters in diameter, that the science team nicknamed blueberries for their appearance in false color images, though their actual color was closer to a dark gray. These spherules were found both embedded within the rock and scattered loose across the ground, where erosion had freed them from their matrix. And their composition turned out to be rich in hematite, an iron oxide mineral that can form in several ways, but which often indicates the presence of water during its formation. The spherules appeared to be concretions, objects that had grown within the rock as mineral-rich water percolated through the sediments long after they were deposited, precipitating iron compounds in small nodules that gradually expanded outward from central nucleation points. But perhaps the most compelling evidence came from the small cavities that pockmarked the surfaces of the rocks, holes that geologists call vugs, which had a distinctive appearance, suggesting they had formed when crystals once embedded in the rock had dissolved away, leaving behind empty molds of their former shapes. The shapes of these vugs were consistent with minerals that form in evaporating water, salts that crystallize as briny liquid dries up, and then later dissolve when water returns, leaving behind the ghostly impressions of their former presence. The spectrometers aboard Opportunity added another piece to this puzzle when they detected the mineral jarosite within the rocks of Eagle Crater. Jarosite is an iron sulfate mineral with a very specific origin, for it forms only in the presence of acidic water, and its detection on Mars was significant because it meant not merely that water had once existed, but that the chemistry of that water could be constrained with some confidence. The water that had touched these rocks had been acidic and had contained dissolved sulfur compounds, creating an environment that would have been quite harsh by earthly standards, but which nonetheless represented liquid water on a planetary surface. A precious and remarkable thing. Over the following months and years, as Opportunity's 90-day mission extended into seasons and then into years, the rover continued its slow traverse across the plains of Meridiani Planum, examining more outcrops, more craters, more evidence of this ancient watery world. Each new exposure of bedrock told essentially the same story, of sediments deposited in shallow, acidic, briny water, then buried, then exhumed by the slow work of erosion over billions of years. The water had not been pleasant water, not the sort of clear, fresh liquid we might imagine when we think of earthly lakes and streams, but it had been water nonetheless, moving and evaporating and leaving behind its chemical signature in the minerals that remained. Meanwhile, on the other side of Mars, Spirit was conducting its own investigations in Gusev crater, a large impact basin that scientists had selected as a landing site because orbital images suggested it might once have contained a lake, fed by a large channel that appeared to drain into the crater from the southern highlands. The hope had been that Spirit would find sedimentary rocks similar to those Opportunity was discovering, lakebeds preserving the record of standing water. But Gusev crater proved to be more complicated than expected. The floor of the crater was covered with volcanic basalt, dark rocks that appeared to have flooded across the surface long after any lake might have existed, burying whatever sediments might lie beneath. Spirit's early traverse found mostly these volcanic materials, and for a time it seemed as though the crater might not yield the watery evidence scientists had hoped to find. Then Spirit reached a low plateau called Home Plate, a roughly circular feature about 90 meters across that rose slightly above the surrounding terrain. And here the story became more interesting. The rocks of Home Plate were volcanic in origin, but they showed signs of having been altered by water, their original minerals transformed by chemical reactions that could only have occurred in the presence of liquid. Some scientists interpreted the layered structure of Home Plate as the remnants of explosive volcanic activity, perhaps steam-driven eruptions where hot magma had encountered groundwater or surface ice, creating violent explosions that deposited fine-grained ash across the landscape. More intriguing still was the possibility of hot springs, places where geothermally heated water might have risen to the surface, creating localized environments where liquid water persisted even as the broader Martian climate grew cold and dry. Such environments on Earth are havens for microbial life, oases of warmth and chemical energy that support thriving ecosystems even in otherwise hostile settings. And the thought that similar environments might once have existed on Mars was a tantalizing one for those who wondered about the possibilities of Martian biology. In 2005, Spirit examined an outcrop called Comanche, located on the flanks of a feature called Husband Hill within Gusev crater. And here, the rover's instruments detected something unexpected: a significant concentration of magnesium iron carbonate minerals embedded within the rock. This discovery was notable because carbonate minerals form under very different conditions than the sulfate minerals Opportunity had been finding at Meridiani Planum. Carbonates typically require water that is neutral or slightly alkaline in pH, water that is not acidic, and their presence at Comanche suggested that Mars had experienced a diversity of watery environments, not just the harsh acidic conditions recorded elsewhere. The Comanche carbonates indicated that at least some Martian water had been relatively benign, closer in chemistry to the waters we might find in earthly streams or lakes, the sort of water that would be more hospitable to the delicate molecular machinery of living things. This was an important finding because it expanded the range of potentially habitable environments that might have existed on ancient Mars, suggesting that the planet's watery past included gentler conditions alongside the more aggressive acidic settings. Years later, after Opportunity had traversed many kilometers across the Martian surface, visiting craters of increasing size and examining ever older layers of rock, the rover arrived at a location called Esperance, a patch of rock along the rim of Endeavour crater that would yield yet another piece of the watery puzzle. The instruments detected clay minerals within this rock, a type of mineral called smectite, which forms through the prolonged interaction of water with volcanic rock. And the chemistry of these clays indicated something remarkable about the water that had created them. The water at Esperance had been neutral in pH, neither acidic nor alkaline, the sort of water that would be drinkable by earthly standards, the sort of water in which the biochemistry of terrestrial organisms could function comfortably. This was the most habitable environment the rovers had yet discovered, a place where ancient Martian water had possessed the gentle chemistry that life as we know it requires. And the discovery added another dimension to the emerging picture of Mars as a world that had once offered multiple opportunities for biology to take hold, if biology ever did arise there. Throughout all of these discoveries, there was a gentle irony at work, a quiet joke that the universe seemed to be playing on the mission planners. The rovers had been designed to operate for 90 days, a duration chosen based on the expected accumulation of dust on their solar panels and the harsh thermal cycling that the Martian environment would impose on their electronics. 90 days was considered an ambitious goal, a reasonable lifetime for machines operating so far from home with no possibility of repair or maintenance. But 90 days came and went, and the rovers continued to function. A year passed, and then another, and still the machines persisted, their solar panels occasionally cleaned by passing dust devils, their electronics proving more resilient than anyone had dared to hope. Spirit would operate for over 6 years before becoming stuck in soft soil and eventually falling silent in 2010. Its batteries finally depleted during the cold Martian winter. Opportunity would continue for nearly 15 years, traversing more than 45 kilometers across the Martian surface before a global dust storm in 2018 blocked the sunlight its solar panels needed to survive, ending a mission that had exceeded its planned duration by a factor of more than 50. Each new discovery along the way had raised new questions, and each new question had justified extending the mission a little longer. Visiting one more crater, examining one more outcrop, reading one more chapter in the 4-billion-year-old story written in the Martian rocks. The careful, patient movements of these robotic geologists never hastened, never rushed toward dramatic conclusions, but simply continued their methodical work, grinding into rock surfaces, pressing spectrometers against stone, capturing microscopic images of textures too small for human eyes to see from Earth. The story they uncovered was one of transformation, of a planet that had begun its existence with water flowing across its surface, pooling in craters, seeping through sediments, altering minerals, depositing salts, and then gradually losing that water to space and to the subsurface, drying out over hundreds of millions of years until it became the cold desert we observe today. The watermarks remained, preserved in the chemistry of minerals and the geometry of sedimentary layers, waiting patiently for billions of years until two small machines from Earth arrived to read them, slowly and carefully, taking all the time they needed to understand what the rocks had to say. The long marathon in silence began, as so many remarkable things do, without any particular fanfare or announcement, simply as an accumulation of days that stretched into weeks, and weeks that gathered themselves into months, until the mission planners and engineers back on Earth found themselves in the curious position of caring for two small robots that had, by all reasonable estimations, already outlived their expected lifespans several times over. The original mission parameters had called for 90 Martian days of operation, perhaps a bit more if circumstances proved favorable. And yet, here were Spirit and Opportunity, still trundling across the rusty terrain, still sending back their patient streams of data, still responding to commands beamed across the vast darkness of interplanetary space. It was the sort of quiet persistence that does not make for dramatic headlines, but does, in its own unhurried way, speak to something rather profound about both the machines themselves and the people who had built them with such careful attention to detail. Spirit, having landed in Gusev crater in January of 2004, began her long traverse across a landscape that had once, perhaps billions of years ago, held liquid water in quantities sufficient to carve channels and deposit sediments. The crater itself stretches approximately 166 kilometers in diameter, a vast depression named after a Russian astronomer, and Spirit's task was to explore what scientists hoped might be the remnants of an ancient lakebed. The early months of the mission revealed a surface strewn with volcanic basalt, which was not quite what the researchers had anticipated. But science often proceeds by way of such gentle surprises, and Spirit continued her methodical examination of rocks and soil with the same steady determination she had shown from the very beginning. As the mission extended well beyond its original 90-day scope, Spirit turned her attention toward a range of low hills visible on the horizon, features that had been noted in orbital imagery but never explored at ground level. These hills, rising modestly above the crater floor, represented a significant navigational challenge for a rover designed primarily for relatively flat terrain. But the engineering team calculated the slopes to be within acceptable parameters, and so Spirit began her slow ascent. The largest of these elevations was subsequently named Husband Hill, in honor of Rick Husband, who had served as commander of the Space Shuttle Columbia and who, along with his 6 crewmates, had been lost during the vehicle's re-entry into Earth's atmosphere on the first day of February 2003. It seemed fitting, somehow, that a small robot climbing through the thin Martian air should carry with her this quiet memorial to those who had ventured into space and not returned. The climb to the summit of Husband Hill was neither swift nor straightforward, requiring Spirit to navigate around obstacles, backtrack when slopes proved too steep, and pause periodically to recharge her solar panels in the weak Martian sunlight. The elevation gain amounted to roughly 82 meters, which may not sound particularly impressive by terrestrial standards, but represented a considerable achievement for a vehicle weighing just under 200 kilograms and standing no taller than a medium-sized dog. From the summit, Spirit's cameras captured panoramic views of the surrounding terrain, images that would later be assembled into breathtaking mosaics showing the curved horizon of a small, cold world stretching away in all directions under a butterscotch sky. Over the course of her operational life, Spirit covered a total distance of approximately 7.73 kilometers, which translates to just under 5 miles in more familiar units. This figure may seem modest compared to the daily commutes that many of us undertake without a second thought. But every centimeter of that distance was traveled on another planet, across a surface no human foot had ever touched, using wheels that had been designed and built more than 100 million miles away. The journey was accomplished at speeds measured in centimeters per second, with frequent stops for scientific observations, and represented a remarkable accumulation of small increments over more than 6 years of operation. Opportunity, Spirit's twin, was meanwhile conducting her own extended exploration on the opposite side of Mars, in a region known as Meridiani Planum. This relatively flat expanse of equatorial terrain had been selected as a landing site because orbital spectrometers had detected the presence of hematite, an iron oxide mineral that on Earth often forms in the presence of water. Opportunity's initial findings confirmed this scientific intuition, revealing layers of sedimentary rock and small spherical concretions that came to be known, with gentle informality, as blueberries. But what made Opportunity's mission truly extraordinary, beyond even these significant geological discoveries, was the sheer distance she would eventually travel. By the time Opportunity's odometer finally stopped accumulating, she had covered 45.6 kilometers of Martian terrain, a distance roughly equivalent to a terrestrial marathon, and then some. No wheeled vehicle had ever traveled so far on any world beyond Earth, and the record-breaking nature of this achievement was marked with appropriate solemnity by the mission team, who paused to note the milestone before continuing with their work. Opportunity's great odyssey took her from her initial landing site, through a series of craters of increasing size, and ultimately toward the rim of Endeavour crater, a vast impact structure some 22 kilometers in diameter. The journey to Endeavour required years of patient driving, with the rover team carefully plotting routes around impassable dunes and treacherous terrain. And when Opportunity finally reached the crater's edge in August of 2011, she had already exceeded her original 90-day mission by more than 7 years. The longevity of both rovers depended critically on their ability to generate electrical power from the weak Martian sunlight, and this dependence made each approaching winter a period of some concern for the mission teams. Mars, like Earth, is tilted on its axis, which means that it experiences seasons as different hemispheres receive more or less direct solar illumination. For a solar-powered rover operating in the planet's southern mid-latitudes, winter brought not only colder temperatures but significantly reduced energy production, as the sun tracked lower across the sky and provided fewer hours of usable light each day. Opportunity developed a particularly clever strategy for surviving these lean months, one that emerged from careful analysis of the terrain and thoughtful planning by the rover drivers back on Earth. By positioning herself on north-facing slopes, Opportunity could tilt her solar panels toward the winter sun, much as a person might angle a deck chair to catch the last warming rays of an autumn afternoon. This tilting technique allowed the rover to maintain sufficient power generation even as the sun dipped toward its lowest seasonal arc. And Opportunity successfully weathered multiple Martian winters through this combination of careful parking and patient waiting. Nature also provided assistance in ways that no one had anticipated during the mission planning stages. Mars is a dusty world, and over time, the fine particles suspended in the thin atmosphere gradually settled onto Opportunity's solar panels, reducing their efficiency and threatening to shorten the rover's operational lifespan. But Mars is also a world of wind, and periodically great spinning columns of air would sweep across the plains, lifting dust from the surface and, occasionally, from the surfaces of small robots that happened to be in their path. These dust devils, as they are called, serendipitously cleaned Opportunity's solar panels on multiple occasions, restoring power generation to levels not seen since the early days of the mission. The phenomenon was observed directly by Opportunity's cameras, which captured images of the swirling vortices passing nearby, and the correlation between these events and sudden improvements in electrical output became one of the pleasant surprises of the extended mission. Spirit, unfortunately, was not so fortunate in the end. In April of 2009, while traversing a region of relatively soft soil near a plateau called Home Plate, Spirit's wheels broke through a thin crust and became mired in a loose, powdery material that provided no traction for escape. The site was designated Troy, and for the next several months, the mission team worked methodically to extract the rover from her predicament. They tested various drive sequences using engineering models on Earth, attempting to replicate the soil conditions and identify a combination of wheel movements that might free the trapped vehicle. They tried driving forward, driving backward, and various diagonal approaches, all while carefully monitoring Spirit's power levels and the integrity of her wheels, one of which had already failed and was being dragged uselessly through the soil. Despite these determined efforts, Spirit remained stuck, her wheels churning the fine Martian dust without gaining purchase, gradually digging herself deeper rather than climbing free. The rescue attempts continued through the autumn and into the winter of 2009. But by January of 2010, the mission team had to acknowledge that Spirit would not be moving again. She was reclassified as a stationary research platform, and plans were made to continue scientific operations using her remaining functional instruments. But Spirit's position was not favorable for surviving another Martian winter, and her solar panels could not be tilted toward the sun. As the days shortened and the available power dwindled, Spirit fell silent. The last communication from Spirit was received on Earth on the 25th of May, 2010. A routine transmission indicating that the rover was entering a low-power hibernation mode from which she was expected to emerge when conditions improved. But conditions did not improve sufficiently, or perhaps some critical component failed in the months of cold and silence that followed. And Spirit never responded to the recovery attempts that continued through the following year. On the 25th of May, 2011, NASA officially ended efforts to contact the rover, acknowledging that Spirit's remarkable journey had come to its conclusion in a small patch of soft soil on the other side of the solar system. Opportunity continued her explorations for 8 more years, outliving her twin by a significant margin and continuing to return valuable scientific data from the rim and environs of Endeavour crater. She studied rock formations that told stories of ancient water, took photographs of the Martian sky and surface with unflagging diligence, and generally conducted herself as if unaware that she had exceeded her design specifications by a factor of more than 50. But in May of 2018, Martian weather began to take a turn that would prove, ultimately, to be beyond even Opportunity's considerable powers of endurance. A dust storm that had begun as a small disturbance in a distant region of the planet began to expand with unusual rapidity, lifting vast quantities of fine particles into the atmosphere and spreading them around the globe. By June, the storm had grown into one of the most significant dust events ever observed on Mars, encircling the entire planet in a thick haze that blocked virtually all sunlight from reaching the surface. For a solar-powered rover, this represented an existential threat, as there was simply no way to generate the electrical energy needed to maintain critical systems. Opportunity's last communication was received on the 10th of June, 2018, a data transmission indicating that her battery levels had fallen dangerously low and that the ambient light levels had dropped to values never before recorded by the rover's sensors. The popular paraphrase of this final message suggests that Opportunity reported her battery was low and that it was getting dark. And while this wording represents an interpretive simplification of the actual telemetry data, it captures something essentially true about the rover's final circumstances. Opportunity was indeed experiencing both an energy crisis and a loss of light, and she was reporting these conditions back to her distant handlers with the same factual precision she had employed throughout her 15 years of operation. When the global dust storm finally subsided in September of 2018, the mission team began an intensive effort to re-establish contact with Opportunity. They sent commands designed to prompt the rover to respond, varied the parameters and timing of their transmissions to account for possible clock errors or antenna misalignments, and listened patiently for any signal that might indicate the rover had survived her long ordeal in darkness. These recovery attempts continued through the autumn and winter, employing every technique the team could devise, but the airwaves remained silent. On the 13th of February, 2019, NASA announced that the Opportunity mission had concluded, and that no further attempts would be made to contact the rover. There was no dramatic ceremony, no sudden revelation, merely the quiet acknowledgement that a small machine on a distant world had completed her work and would not be returning home. The silence that followed was not empty, but full, containing within it the memory of nearly 46 kilometers of patient exploration, of 15 years of faithful service, of countless images and measurements transmitted across the void to satisfy human curiosity about worlds beyond our own. And so we come now to the larger meaning of all those years spent rolling across the rust-colored plains, all those patient measurements and careful photographs, all those quiet nights when the rovers slept beneath alien stars while their data traveled home at the speed of light. What Spirit and Opportunity found in the rocks and soils of Mars was not simply interesting geology, not merely curious chemistry, but something that rewrites the story of two worlds at once, our own blue Earth and that distant ochre neighbor that has so long captured our imagination. The rovers discovered, with the slow accumulation of evidence that is the hallmark of careful science, that Mars was once a fundamentally different place, a world where water pooled and flowed and perhaps sustained the conditions necessary for life itself. And this discovery changes how we understand not just Mars, but the possibilities of the universe entire. To appreciate what the rovers found, we must journey back in time, not millions of years, but billions, to an era geologists call the Noachian period, named for Nokis Terra, one of the most ancient terrains on the Martian surface. This period stretched from approximately 4.1 billion years ago to around 3.7 billion years ago, a span of some 400 million years when the solar system itself was still relatively young and both Earth and Mars were finding their way toward whatever fates awaited them. During this Noachian age, the evidence now suggests Mars was a remarkably different world from the cold desert we observe today, a world where the atmosphere was thicker, where temperatures were warmer, and where liquid water existed on the surface in quantities sufficient to carve valleys, fill basins, and create the chemical conditions we associate with habitability. The evidence for this ancient wet Mars accumulated through the patient work of Spirit and Opportunity, like sediment building up in a quiet lake. Spirit, exploring the Columbia Hills, found rocks that bore the unmistakable signatures of alteration by water, minerals that could only form when liquid water interacted with volcanic rock over extended periods. Opportunity, wandering the plains of Meridiani, discovered sedimentary stones laid down in shallow, briny waters, complete with the rippled textures and embedded spherules that spoke of aqueous processes operating over geological timescales. Together, the rovers painted a picture of ancient Mars as a world where water was not a rare visitor, but a persistent presence, where lakes and perhaps even seas existed for hundreds of millions of years, long enough for the slow processes of chemistry and geology to work their patient transformations. This brings us to what scientists call the habitability question, a term that requires some gentle unpacking for those of us settling in for the evening. When astrobiologists speak of habitability, they do not necessarily mean that a place was inhabited, that life actually arose and flourished there, but rather that the conditions existed which, as far as we understand life, would have permitted it to exist. The requirements are straightforward enough: liquid water, a source of energy, and certain chemical building blocks such as carbon, nitrogen, phosphorus, and sulfur. What Opportunity found at Meridiani Planum and what Spirit found in the Columbia Hills was evidence that all these requirements were once met on Mars, that for a substantial portion of the Noachian period, the red planet possessed the necessary ingredients for microbial life as we understand it from our studies of Earth. This does not mean, of course, that life did arise on Mars, and we should be careful not to leap ahead of the evidence in our drowsy contemplation. What the rovers established was possibility, not proof. The existence of an environment where terrestrial microorganisms could have survived and perhaps thrived, had they been present? The actual question of whether Mars ever hosted living things remains open, a mystery that subsequent missions continue to investigate with ever more sophisticated instruments. But the rovers shifted the question from whether Mars could have been habitable to whether it actually was inhabited, a subtle but profound change in the nature of our inquiry, a narrowing of the vast unknown into a more tractable puzzle. The story of Mars is also, in its way, a cautionary tale about the fragility of worlds. For the evidence suggests that the red planet was not always destined for its current frozen desolation. The transformation of Mars from a potentially habitable world to the cold desert we observe today appears to be intimately connected to the loss of its global magnetic field, an event that occurred early in Martian history and left the planet vulnerable to the relentless erosion of its atmosphere by the solar wind. On Earth, our planet's liquid iron core generates a powerful magnetic field that extends far into space, deflecting the charged particles streaming from the sun and protecting our atmosphere from being gradually stripped away. Mars, being smaller than Earth, cooled more rapidly, and its internal dynamo shut down perhaps as early as 4 billion years ago, leaving the planet without its protective shield. Without this magnetic field, the solar wind began its slow work of atmospheric erosion, carrying away particles of the Martian atmosphere one by one, year after year, for billions of years. The evidence for this ongoing loss can be seen in the ratio of deuterium to hydrogen in what remains of Martian water, a measurement that tells a story of profound change. Deuterium is a heavier isotope of hydrogen, containing 1 proton and 1 neutron rather than just 1 proton, and when water escapes from a planet's atmosphere, the lighter, ordinary hydrogen escapes more readily than the heavier deuterium. Over time, this selective loss enriches the remaining water in deuterium, leaving a telltale signature of atmospheric escape. On Mars, measurements by orbiting spacecraft have found deuterium to hydrogen ratios significantly elevated compared to Earth, suggesting that the planet has lost perhaps 80% or more of its original water inventory to space, a vast amount of the very substance that once made the planet potentially habitable. This understanding of how Mars lost its water and its thick atmosphere has implications beyond the red planet itself, for it illuminates the factors that determine whether any world can maintain conditions suitable for life over the long timescales that evolution seems to require. The rovers, by establishing that Mars was once wet, helped to frame the question of why it became dry, and this question leads to considerations of planetary size, internal heat, magnetic field generation, and distance from the parent star. In studying Mars, we learn something about what makes Earth special, about the delicate balance of factors that has allowed our own world to remain habitable for 4 billion years and counting, and about what we might look for when we search for habitable worlds around other stars. The legacy of spirit and opportunity extends beyond the scientific knowledge they gathered to the technological innovations they pioneered, innovations that continue to guide their successors across the Martian surface. Among the most significant of these was the development of autonomous navigation algorithms that allowed the rovers to drive themselves across terrain without waiting for instructions from Earth. Given the communication delay between the two planets, which varies from about 4 minutes to over 20 minutes, depending on orbital positions. Traditional remote control would have been hopelessly inefficient, with the rover spending most of its time waiting for commands. Instead, engineers at the Jet Propulsion Laboratory developed sophisticated software that could analyze images from the rover's cameras, identify hazards such as rocks and slopes, and plot safe paths through challenging terrain, all without human intervention. These autonomous navigation capabilities, proven over years of operation on Spirit and Opportunity, were refined and enhanced for subsequent missions. The Curiosity rover, which landed in 2012, and the Perseverance rover, which arrived in 2021, both benefited enormously from the lessons learned by their smaller predecessors. The ability to drive longer distances in a single day, to negotiate more challenging terrain, and to respond to unexpected obstacles all trace their lineage back to the algorithms developed for the Mars exploration rovers. In this way, Spirit and Opportunity continue to explore Mars through their technological descendants. Their software, DNA, living on in the systems that guide new rovers across landscapes they never themselves could reach. There is another legacy, perhaps less tangible, but no less real, in the way the rovers captured the human imagination and inspired a generation of young people to look upward and dream of distant worlds. When NASA offered the public the opportunity to send their names to Mars on a small DVD carried by Opportunity, more than 16 million people from around the world responded, their names etched in microscopic text on a disk that now sits on the rim of Endeavour crater, a monument to human curiosity on an alien shore. Children who wrote their names on that DVD are now adults, some of them working as scientists and engineers on the very missions that carry forward the work the rovers began. The power of exploration to inspire, to kindle wonder, to draw young minds towards science and discovery. This, too, is part of what Spirit and Opportunity accomplished in their years on Mars. Among the most intriguing features discovered by Opportunity were the small spherules that came to be known as blueberries. Those centimeter-sized balls of grey hematite scattered across the surface of Meridiani Planum and embedded in the sedimentary rocks there. As we discussed earlier, these spherules formed through the action of groundwater moving through the sediments, precipitating iron minerals in concentric layers around some nucleus. But the precise conditions of their formation and their implications for Martian history remain subjects of ongoing scientific discussion. Some researchers have noted that on Earth, similar iron oxide concretions can form through biological processes, with microorganisms playing a role in the precipitation of iron minerals from solution. This has led to speculation about whether the Martian blueberries might represent potential biosignatures, evidence of ancient microbial activity preserved in stone. The scientific consensus, it must be said, currently favors a purely geological explanation for the blueberries, with abiotic chemical processes fully capable of producing such features without any involvement of life. The iron-rich groundwater, the porous sediments, the passage of time, these are sufficient to explain what Opportunity observed, and the principle of parsimony suggests we should not invoke life when simpler explanations suffice. Yet, the debate continues in a quiet way. with some researchers pointing to subtle features of the blueberry's distribution or composition that they argue are more consistent with biological involvement. This is how science often works, with competing hypotheses slowly being tested against accumulating evidence, with no dramatic resolution, but rather a gradual convergence toward understanding that may take decades to achieve. What we can say with confidence is that the blueberries, whatever their origin, speak to a Mars where water persisted in the subsurface for extended periods, where the chemistry was dynamic and complex, where the conditions for life might well have been met even if life itself never arose. They are, in their small spherical way, ambassadors from an ancient Mars that was far more Earth-like than the planet we see today. A world where the fundamental prerequisites for biology as we know it were present and waiting. Whether anything ever took advantage of those conditions remains one of the great unanswered questions of our time, a mystery that future missions may help to resolve. And so the rovers changed our understanding of two worlds, showing us a Mars that was once warm and wet and possibly habitable, while simultaneously illuminating, by contrast, the special circumstances that have allowed Earth to remain a living world. They showed us how planets can lose their atmospheres when magnetic shields fail, how water can escape to space over billions of years, how the promise of habitability can fade into frozen silence. They develop technologies that continue to explore long after their own treads have stilled, and they carried the names and hopes of millions to a world that ancient humans could only wonder at from afar. The story of spirit and opportunity is, in the end, the story of human curiosity reaching across the void to touch another world, to read the records written in stone, and to learn something true about the universe we inhabit together. Human and robot, Earth and Mars, all of us drifting through the cosmic dark, seeking to understand. And so we come to rest, as all things do, in the quiet that follows great journeys. Somewhere on Mars, in a crater called Gusev that was once perhaps a lakebed billions of years ago, a small rover named Spirit sits motionless beneath a thin veil of rusty dust. Its wheels, which carried it across more than 7 kilometers of rocky terrain over the course of 6 Earth years, became trapped in soft soil near a low plateau called home plate, and there the rover remained, tilted slightly to one side, its solar panels no longer able to gather enough of the distant sunlight to keep its systems warm through the long Martian winter. The last signal from Spirit arrived on Earth in March of 2010, and despite many months of patient listening, of sending gentle commands across the void in hopes of a reply, the rover never spoke again. And so it rests there still, its cameras pointed forever toward the Columbia Hills that it spent so many years exploring, those modest peaks that rise from the crater floor like memories of ancient upheavals, named in honor of the 7 astronauts who perished when the Space Shuttle Columbia broke apart during re-entry in February of 2003. There is something worth knowing about the memorial that Spirit carries, something that connects this small machine to human loss and human remembrance in a way that feels both solemn and tender. Mounted on the back of Spirit's high-gain antenna is a small aluminium plate, placed there before launch as a tribute to the Columbia crew. And on this plate are engraved the likenesses of the 7 astronauts alongside an image of the shuttle itself in flight, with the American flag and the words that acknowledge their sacrifice and their contribution to exploration. The names are there, etched into metal that now sits beneath Martian skies. Rick Husband and William McCool and Michael Anderson and David Brown and Kalpana Chawla and Laurel Clark and Ilan Ramon, each of them remembered not only on Earth, but on another world entirely. Their memorial standing in the thin atmosphere of a planet they never had the chance to visit. And perhaps there is something fitting in this, that a rover sent to explore would carry with it the memory of those who also ventured outward, who also accepted the risks that come with pushing beyond the familiar boundaries of home. Spirit's cameras, the ones that captured so many thousands of images of rocks and soil and distant horizons, now gaze out at a landscape they can no longer record. The panoramic camera assembly sits atop its mast like a head tilted slightly in contemplation, and though the lenses have long since lost their power to see, they remain oriented toward the hills that the rover climbed with such determination, grinding slowly up slopes that no one had ever expected a wheeled robot to navigate. The winds of Mars continue to blow across this scene, carrying fine particles of dust that settle grain by grain upon the rover's surfaces, slowly softening its angular form, slowly blending it into the landscape it worked so hard to understand. In time, perhaps many thousands of years from now, Spirit may become little more than a vague shape beneath the regolith, a slight mound that future visitors might walk past without realizing what lies beneath, unless they know to look, unless they carry maps that mark the resting places of these early pioneers. Across the planet, on the opposite side of Mars, another rover sleeps in a valley that bears a name chosen with hopeful foresight. Perseverance Valley cuts into the rim of Endeavour Crater, a wide and ancient impact basin that Opportunity spent years traversing to reach, driving kilometer after kilometer across the flat plains of Meridiani Planum, past countless small craters and scattered meteorites and endless fields of the iron-rich spherules the science team affectionately called blueberries. The rover arrived at Perseverance Valley in the spring of 2017, intending to study the channel-like feature for clues about how water may have once flowed there, carving into the rock in some distant epoch when Mars was warmer and wetter than the cold desert it has become. And it was there, working its way slowly down the slope, that Opportunity encountered the dust storm that would prove to be its last. The storm began in late May of 2018 as a small disturbance in the Arabia Terra region, far from where Opportunity was working, but within weeks it had grown into something immense, a planet-encircling event that wrapped Mars in an ochre shroud so thick that the sun became invisible from the surface. For a rover that depended entirely on sunlight to power its systems, this darkness was a grave concern, and the team on Earth watched anxiously as the power levels dropped, as the little robot reported less and less energy available for its heaters and its computers and its radio. The last communication came on June 10, 2018, a brief status report indicating that the battery charge had fallen dangerously low and that the rover was entering a low-power fault mode, a kind of protective hibernation designed to preserve whatever energy remained. And then, silence. The storm raged on for months, slowly depositing layer upon layer of fine dust across every surface on Mars, including the solar panels that Opportunity needed to wake again. When the skies finally cleared in September, the team began their recovery efforts, sending commands that would prompt the rover to respond if it could hear them, playing songs across the radio link in a gesture that was equal parts technical strategy and emotional farewell. They chose songs about waking up, about coming home, about not giving up, and they transmitted these musical messages hundreds of times over the following months, hoping that somehow the rover's panels had been cleaned by wind, that its batteries had recharged enough to power a reply. But the seasons turned and no signal came, and in February of 2019, the mission was formally concluded. The team gathering one last time to send a final message and to acknowledge what had been accomplished across nearly 15 years of operations on a world that had never been designed to welcome machines or people. Opportunity witnessed 5,352 Martian sunrises during its time on the surface, each one a small miracle of continued survival. Each one an opportunity to photograph the alien dawn and send the image home across millions of kilometers of empty space. The Martian day, or Sol, is only slightly longer than an Earth day, about 40 minutes more, and so the rover's schedule drifted slowly against the rhythms of its human operators, the team adjusting their own sleep patterns to match the rover's waking hours, living on Mars time for weeks or months at a stretch. And each morning, when the rover would rouse itself and turn its cameras toward the eastern horizon, there was a moment of quiet anticipation, a chance to see what no human eye had ever seen directly: the sunrise on another world, the sun appearing smaller and more distant than we know it, the sky taking on colors that range from butterscotch to pink to deep blue as the light filters through dust and thin atmosphere. These images of Martian sunrises, transmitted across the solar system and received by dishes on Earth, became a kind of communion between two worlds. A daily greeting from a robot that had somehow become more than just a collection of wheels and circuits and scientific instruments. People around the world came to know Opportunity, to follow its progress, to celebrate its achievements, and to worry when dust storms threatened or when wheels showed signs of wear. The rover's longevity, so far beyond what anyone had planned or expected, transformed it from a mission into a companion, from an experiment into an ambassador. And when it finally fell silent, there was genuine grief among those who had worked on it and those who had simply watched from afar. Mars continues to turn beneath its distant sun, rotating once every 24 hours and 37 minutes. The same rhythm it has kept for billions of years, long before there were rovers or radio signals or anyone to wonder what lay beyond the evening star that wandered through Earth's ancient skies. The dust storms come and go with the seasons, sometimes small and localized, sometimes vast enough to engulf the entire planet, and through it all the rovers rest in their chosen places, slowly being incorporated into the landscape they came to study. The winds that blow across Gusev crater carry particles that once sat at the bottom of an ancient lake, or perhaps at the shores of a vanished sea, and these particles settle upon Spirit's still cameras and immobile wheels with the same indifference they would show to any other rock or ridge. In Perseverance Valley, the same process unfolds. the fine dust of Mars drifting into every crevice of Opportunity's frame, softening its edges, dimming the reflective surfaces that once glinted in the Martian sun. And yet, there is something hopeful in imagining what might come next, in considering the possibility that one day, perhaps decades from now, or perhaps centuries, human beings will actually stand on Mars and walk across the same terrain that these rovers traversed. There have been many artists' conceptions and many mission proposals and many dreams of a future in which Mars is not just a destination for robots, but a place where people live and work and explore in person. And in these visions, almost invariably, there is a scene in which astronauts make a pilgrimage to the rovers, seeking out the locations where Spirit and Opportunity came to rest, paying their respects to the machines that came before and made the way a little less unknown. One can imagine the moment when a suited figure first stands beside Spirit, brushing away the dust that has accumulated over years or decades, revealing the cameras and the wheels and the memorial plaque that honors the Columbia crew. Perhaps this future explorer will take a photograph of their own, adding to the archive of images that documents humanity's gradual expansion into the cosmos. A picture of a person and a robot together on a world that was once considered utterly beyond reach. And perhaps, eventually, the rovers will be carefully lifted from their resting places and transported to museums, either on Mars or on Earth or on stations orbiting between, where future generations can see for themselves the small machines that accomplished such remarkable things with such limited resources. These rovers changed how we think about ourselves, not through any single discovery or any dramatic announcement, but through the slow accumulation of evidence that we are capable of reaching across unimaginable distances with patience and care. Before Spirit and Opportunity, Mars was primarily a subject for telescopes and brief flyby missions, a world glimpsed from afar and understood only in broad strokes. After them, Mars became a place with geography and weather and local variations, a place where certain rocks tell stories about ancient water and certain minerals suggest that conditions might once have been suitable for life. The rovers did not answer every question, and they raised many new ones, but they demonstrated that careful, sustained exploration is possible, that we can send our instruments and our curiosity to other worlds and learn what we could never learn from Earth alone. We are no longer only stargazers, looking up at the night sky and wondering what might be out there. We have become explorers in a deeper sense, beings who reach across the void with machines built from our understanding of physics and chemistry and engineering. Machines that carry our questions and return with answers we could not have anticipated. The rovers were expressions of hope, tangible evidence that human beings can choose to learn rather than to fear, to investigate rather than to ignore, to send our best instruments and our most careful thinking to places we cannot yet visit ourselves. And in doing so, they expanded not just our knowledge of Mars, but our sense of what is possible, our confidence that the future might include journeys even more ambitious and destinations even more distant. The two small robots that landed on Mars in January of 2004 changed the story we tell ourselves about who we are and what we can accomplish. They showed us that exploration does not require drama or spectacle, that the most profound achievements can unfold quietly over years of patient work. one photograph at a time, one rock at a time, one sunrise at a time. And now, as they rest beneath the accumulating dust of a world they helped us understand, they remain monuments to curiosity, to persistence, to the gentle human impulse that looks at a distant light in the sky and wonders what it would be like to go there, to see for ourselves, to know what has never been known before. We are dreaming forward now, as we have always done, imagining missions that will build on what the rovers taught us, planning for the day when human footprints will mark the Martian soil. And somewhere in those dreams, in the visions of what is yet to come, there is a quiet acknowledgement of the machines that went first, the patient explorers that rolled across alien landscapes and sent home what they found, asking nothing in return except the chance to keep going, to keep seeing, to keep learning for as long as their systems allowed. They were good machines, made by good people who cared about what they were doing, and they accomplished more than anyone had dared to hope. And now they sleep, as we all will sleep eventually, their work complete, their legacy secure, dreaming whatever dreams machines might dream on the distant plains of Mars.